So despite the many complications involved and the absurd price, I think my favourite thing that I've done to the mill is add that 3 horsepower motor to the top of the spindle. You know, even 2 years later, it looks so over the top, but you really can't argue with the results. I mean, it is a bit of a monster. Just no way you could do that or anything close to it with the original 1 horsepower DC motor. Despite all that though, you could argue that the 1 horsepower motor on the lathe has more torque. Or at least more torque at the spindle, depending on the RPM. I'd argue that once you drop below about 700 RPM, the lathe has way more usable torque than you would get at the same RPM on the mill, and that's despite it only having 1 horsepower and the mill having 3. And the reason for that should be rather obvious. The lathe runs a fixed speed AC motor, and it uses a gearbox to gear the speed down, which in turn also ups the torque at the spindle. The motor spins at about 1400 RPM, so 700 RPM at the spindle is almost doubling the torque. Minus a little bit because of the efficiency loss, but even still, doubling it is a huge gain. And I've always said this is the big reason why I chose this lathe, simply because it has a gearbox with a ton of speeds. Compare this to the mill, where instead of using a gearbox to change the RPM, the speed is simply reduced by using a VFD, which changes the output voltage and the frequency that goes to the motor, and that works fine enough near the speeds at which the motor is designed to run at. So for this motor, let's say about 1000 to about 1400 RPM. And for the most part, that is fine for most of the endmills and the drills that I use, but once you start to use bigger tooling and you need to drop that RPM to say 600 or 700 RPM and below, you start to lose efficiency and torque, and it really doesn't take that much to stall the motor out. And that's sort of regardless of it having 3 horsepower or not. And that's why sometimes I need to run my tooling a bit faster than I really would want to, simply because I don't have the torque at the RPM where the tool really wants to be running. A really good example is that I'm running this at about 80 to 100 RPM and I can easily stop it simply by grabbing it. And if I tried to do the same thing on the lathe with its 20 times torque multiple, I'd probably break my wrist. Now the thing is, there are compensation settings on the VFD to help it boost its torque at lower RPM, but the VFD that I'm using is a cheaper one. Well, though I say that, it was about $400, but even so, the results weren't as impressive as you could get from a more expensive VFD. And I guess that brings us to this project. Now the thing is, I'm not looking to overcomplicate things here. All I'm really aiming to do is to try and add some sort of speed reduction through the belts, simply so we can step the speed down and hopefully get an increase in torque. So first things first, let's get it pulled apart and see what we're dealing with. And unfortunately that means ripping the motor off, which also means having to unwire the whole thing. Okay, so what we have here are really the guts of the mill. So what we have here is our driver pulley, which I made up years ago in a hurry, and really it was supposed to be replaced a long time ago. So this one here is definitely being replaced. And then we have our driven pulley, which also incorporates a spline into it, which matches with the spline on the spindle, which drives the spindle. And it's all held in this bearing housing, and it's all held in place by a set of snap rings. And if you really ask me, I never really liked this setup a whole lot. You know, it doesn't hold onto the bearings as well as it should do, and it does cause some knocking sounds that you can hear when the mill is running. What you're hearing is the sound of the bearing assembly moving around ever so slightly because there's no load other than a bit of friction to hold it all in place. And you know, if it was up to me right now, I'd probably rebuild the whole thing, you know, the whole top end assembly of the milling machine, and probably change out the dropper belts at the same time. But that is a lot more work than I really want to do at the moment, and I need a lot more material than simply what I have on hand. So let's just put that project aside for a little bit. Instead, what I want to do is simply to add some sort of step-down pulley assembly that can be easily replicated on your mill if you want to do the same thing. And in fact, with the design that I'm planning on doing, it should be very easy to change it up to either get a step up or a step down in speed and torque. At least that's the plan. So to achieve all this, the first thing we need to do is to modify the driven pulley, which needs to be removed from its assembly. And that is the pulley now cleaned up. I think now you should be able to get a better look at that spline pattern that I mentioned before. If I were to rebuild this, I'd have to recut that spline pattern, and it's not like that it would be an impossible job to recreate that, but it would require a fair amount of custom tooling to be made. And I'm not going to be doing that today, so instead what we need to do is get this in the lathe so I can modify it. The extrusion on the end is a little bit too big for ER32 collets, and I need to get it pretty concentric, so I'll swap out the collet chuck for a 4-jaw chuck. With it now in the lathe and centered, I'll now turn down a flange on the end. This will be used for locating and centering the pulley that will attach to the top. With that now done, I now need 6 holes to be drilled and then tapped. This will be for holding the pulley that will attach onto the top. Now normally in a situation like this, I'd simply use the hole pattern setting on the DRO, but with the mill pulled apart, in fact this is the part that drives the mill, I instead need to do it the old fashioned way and simply mark out the hole pattern by hand using a set of dividers. And that's why I inscribed the hole pattern diameter using the lathe. And once the hole locations are punched, I'll then draw them out on the drill press. And with the holes now drilled, I'll then get them tapped. Now I was a bit apprehensive about holding everything together this way, but in reality it's going to be more than enough holding power, and the motor simply can't produce enough torque to shear the bolts that'll be holding everything together. And with the holes now tapped, that is the driven pulley now done for the moment. Now back at the lathe, I now get the 4-jaw ripped off and replaced with the 3-jaw. I mean technically I could have used the 4-jaw for this, but I really wasn't in the mood for dialing in another piece of stock, and this part does not need to be hugely concentric. So to make the rest of the pulleys, we now have a piece of aluminium. I think it's 6061 grade, which is effectively your normal bog standard aluminium grade. And there should be enough material to get 3 pulleys made from this. I mean, technically, I could have reused the old steel one, but because the tooth pattern is wrong, and for some reason I made it with too many teeth last time, it's been reducing the amount of torque at the spindle for the past 2 years. Now, why I did that, I have no clue, but ultimately, if I'm already making pulleys, it doesn't take a whole lot more effort to make a replacement one, and do it correct the second time round. So as well as replacing that, we also need a large pulley and a small pulley for varying the speeds. I'm also going to be using different inserts this time compared to the last time I machined this aluminium, so fingers crossed that they hold up a little bit better. Okay, so it's not perfect, but it is a huge improvement compared to the old inserts. So with the end now faced off, I'll now start to drill a hole all the way through the aluminium. I'll then follow it up with a 22mm Deming bit. It's far quicker to use this than to bore it all with a boring bar. I'll then come in with a boring bar and bore it to exactly 24mm so it fits perfectly on the motor shaft. And that is pretty much spot on. We'll then swap to a normal cutter and then take the outside diameter down to size. With that now done, I'll start to machine down a 40mm flange on the front. This should be an exact match with the one that we made on the driven pulley. And with that now done, we can now get it parted off. With the first pulley now made, we'll now start to make the second one, since the stock is already in the lathe. So the first thing we'll do is start to bore out the hole. Now this one is going to be slightly larger than the one beforehand, owing to the fact that the drawbar that I'm using on the mill is 27mm in diameter, and the drawbar needs to pass all the way through this pulley. With the bore now done, I now start to machine in a 40mm counter bore on the front face. And this will match up perfectly with the flange on the other two pulleys. And that is a perfect fit. Now because this pulley is going to be quite small and we'd be wasting a lot of material if we simply turned it into chips, what I'm going to do instead is come in with a hole saw and try to save that outside material. Doing this is very slow, but thankfully the lathe has enough torque to be able to do this. And once the saw is at full depth, I'll then come in with a parting blade and then part off that outside material. I'm not exactly sure what I'll do with this piece of aluminium, and it'll probably sit around for about 3 years, but when the day comes that I finally find a use for it, I'll be pretty happy that I have it on hand. As for the rest of the pulley, I can then take it to its final size and then get it parted off. And finally, we can then get the large pulley made. And once again, that is pretty much a perfect fit on the bottom pulley. With the pulley now made, we can then get them in the lathe and then clean up the back of each of them. Alright, and that's the 3 blanks now made. And hopefully at this point you can now get a rough idea of how it all should go together. Essentially, they just stack on top of each other like so. Now normally the plan is to have the large one on the front as a driven pulley. This should give us our gear reduction, but if I want to, the option is always there to very easily swap them around to get a speed increase. And it's very unlikely that I'll ever be doing it, but the good thing is that it gives me options to work with if I really need it. Now the next thing that we need to do is get the mounting holes drilled in and the teeth machined. And to be able to do that, we do need to get the mill put back together. So I'll go over to the press and get the driven pulley pushed back into its assembly, and I'll also fit the old driver pulley back onto the motor. Alright, so you join me back over at the mill. I have the pulley set in the vise, and now I need to drill some holes. First things first, I would have thought that I would have had a V-block suitable for holding this, But as it turns out, I can't currently find it, so for the moment I'll take it easy and hopefully the part shouldn't move in the vise. So the first thing I'll do is find the centre of the pulley, and then I'll use the DRO's hole pattern to drill the holes for mounting it. Now the way that this is going to work is that the large pulley is going to use the 3 outside M8 bolt holes for holding itself onto the bottom pulley, whereas the smaller pulley is going to use the 3 smaller M6 bolt holes. And finally, the middle pulley is going to get the 6 holes drilled and then tapped into it. And with that now done, we can now chuck the dividing head on the mill to cut the teeth. Now to hold the pulleys on the dividing head, I'll turn up an arbor from an old piece of steel. Now to cut the teeth, I previously made up this cutter and holder, which has the correct tooth pattern for the timing belt that I'm using here. And also, rather importantly, the cutter has the correct amount of relief built into it, which means that it shouldn't rub as it's cutting. Now since this is a single point cutter, I am going to have to take it easy with the feed brake. But so far, despite it being a pretty simple tool in terms of geometry, I'm pretty happy with how it's cutting. Now in total, this was probably a 40-minute job for the one small pulley, and it was all going well up until the very last tooth, where I accidentally fed it in a little bit too far, and the cutter crashed into the hardened jaws. Now thankfully it was tempered back enough so that the only damage was to the cutter itself, but unfortunately that cutter is broken, and because it was a custom tool, it is going to need to be remade. And unfortunately, if things weren't already bad, it looks like the cutter itself slipped in the holder because the tooth profile has now slipped down and it's now offset. You can see that's no longer perfectly perpendicular to the center line of the blank itself. So unfortunately, that whole blank is going to have to be redone. It's pretty annoying, but that unfortunately is machining sometimes. Thankfully though, the rest of the pulley seemed to work out just fine, being machined with pretty much no issues at all. With the large pulley now made, I'll get it bolted to the front driven pulley. And before I do the motor pulleys, I do need to make up a steel spacer sleeve, since the hole on the top pulley is made to be a bit larger to accommodate the drawbar when it's mounted on the front. And finally, once it's all mounted and put back in place, this is what it all looks like. Honestly, it was pretty crazy beforehand, but now there is a lot more going on, and it just looks even crazier than it already was. Thankfully, it all seems to be relatively concentric, and everything is holding together quite well. And as an added benefit, with it in its normal configuration, the gear ratio is much closer to being a 1-to-1 ratio compared to the 2-to-3 ratio that it was at before. So I should be getting much more torque at the normal speeds that I'm usually operating at. But if I do need more torque, I can always swap over to the low gear setup. And on a practical level, it's very straightforward to change the speeds. I simply undo the bolts that hold the motor bracket in place, pull the belt up to the next set of pulleys, and then simply bolt it back down. In total, it should take less than a minute to do. With that said though, being able to swap the large and the small pulleys around is a whole nother thing. The motor needs to be pulled off the bracket, which means the bracket itself needs to be pulled off the mill, which requires the wiring also be removed. On a good day, that is easily a 10 to 15 minute job. So don't expect me to be doing that all that often. For the most part, it's always going to be set up with a speed reduction in mind. In terms of working though, it does what it's set out to do. It allows the AC motor to stay in that 1000 to 1400 RPM band, whilst dropping the speed at the spindle and increasing the amount of torque. It's not the endgame solution that I was really looking for because I can still stall it out if I really want to, but I'm getting so much more torque and I'm able to operate the mill in the speeds that the drill bits really want to be working at. And also the mill now has extra torque in the normal setup that I usually run at. You know, I can now run this 30mm drill bit in steel in the normal setup without much issue, and I don't think I would have been able to do that beforehand. All in all, really happy with this setup, really happy with the results, and frankly, if I didn't break the tool the first time round and I didn't waste that first blank, it would have been a really quick project. And that's about it for now. I hope you enjoyed this video, thank you very much for watching, and I'll see you next time.